Okay, everyone. Very good morning, and it's very nice weather at IIT BHU Varanasi, and it's our pleasure to have Professor Shio Kim here from South Korea, and his topic is AI for autonomous vehicles. I'm going to give a very brief introduction about Professor Kim, and we are really delighted to have you, sir, over here. So, Professor Shio Kim is a director, Seamless Transportation Lab and VR Lab, Yonsei Institute of Convergence Technology. He found Cooperative Autonomous Vehicle Research Center, a research center for development of autonomous vehicle and intelligent transportation system. Supported KTS in 2017. His main research interest includes intelligent vehicles, reinforcement learning, and virtual reality. Professor Kim found Reverse Research Center for Advanced Hybrid Electric Vehicle Energy Recovery System, which is a government-supported IT Research Center (ITRC) in 2009. He is also serving as the technical advisor of Grieve Creative Lab, a company developing and providing technologies for mitigating simulator sickness of VR headset and VR contents. Prior to this, he had been working for LG Research Institute and he was a key contributor to system on chip design. Professor Kim is experienced in the patent process and invention development. He has published extensively in referred conferences, journals, and he has organized many major conferences as general chair or program chair. He got more than 50 patents and published more than 100 conference and journal papers. He was the chair of IEEE SSCS Seoul chapter from 2013 to 2015 and a chair of Vehicular Electronics Technical Group in IEEE from 2013 to 2015. Thank you so much, Professor Kim. Now the stage is yours, sir.
Thank you very much for kind introduction.
Thank you.
I'd like to start my lecture today. Okay, I share the lecture slide now.
Sure.
Okay, I hope everyone can see my presentation material.
Yes, we can see it, sir.
Okay.
Please go ahead.
Good morning. Yeah, good morning, everybody. This is Shio Kim. Today's lecture is for the artificial intelligence for autonomous vehicles. I'll do a lecture about 1.5 hours. After my lecture, Dr. Astosh Mishra will do some hand-on practice and some demonstration about 1 hour. Okay, here is the outline of today's lecture. First of all, I will look the automotive industry and market. After that, I will talk about the roadmap of autonomous vehicles and some technical and business challenge and opportunity of AV. And then I will introduce AV technologies developed by my lab. The name of my lab is STL, Seamless Transportation Lab, and I will conclude my talk with some concluding remark. We look at the automotive industry and market. First of all, we may thinking about how big the companies. We can share is a market share of automotive vehicles OEM. Then we can see the big three. The Volkswagen, Toyota, and General Motors. One is for European German company. The other is a Japanese company. The last one is for the famous the US company. These three companies is producing about 10 million vehicles per year. And then you may see that the global vehicle manufacturing, we produce about 100 million vehicles per year. and the global vehicle market is about more than 200 billion US dollar per year. Then you can see the in size. This is a big three in the market. It means it has the larger market share in the automotive industry. And the second, the key, we look at the automotive industry is revenue. Even though the Daimler Benz and the BMW are listed in the market share, the top 10 in the market share, the Daimler is top 3 in the revenue, and the BMW is listed in around the top 7 and top 8 in the revenue. Then it means the Daimler and BMW produce a very luxury car. The unit price of the car is very expensive. Then the popular family car of Volkswagen, Toyota, or General Motors. Then this car is we can see the another category of automotive industry is a brand. Why is 3 different category is important? Currently, the market share and the revenue is very important in current automotive industry. But in the future, if the markets move to the another directions, then maybe there is a big revolutionary change. We expect a big revolutionary change in the automotive industry and market. Then I'll talk after this the mega trend. I revisit this issue again, and there is a 5 mega trend in the automotive industry. Actually, this trend is showing the digital transformation of automotive industry. The first trend is electrified, and it become autonomous, and is shared, and is connected, and also is the system is yearly updated. Then electrified means that there is a revolutionary changing in the energy system. Then from the fuel to the energy, most of vehicle is powered by the electricity. Then electric vehicle will be the main trend. And the autonomous means the AI will be a key role. Then self-driving intelligent vehicle will be the future. And the shared means that there will be a big change in the ownership, the mobility. Instead of the purchasing the private vehicle and using holding the ownership of the vehicle is a current model. But in the future, the mobility as a service will be the major business in the future automotive industry. And the connected means all vehicle is connected by the internet. Maybe it's a 5G cellular, the V2X. V2X means vehicle to everything. And also all the vehicles connected in the internet. Then we call it IoV, Internet of Vehicle will be main. And the yearly update means currently all the vehicle, when you the vehicle manufactured, all the software, you cannot change the software. But the yearly update means we update the software of vehicle very similar to your mobile phone. Like the over-the-air update will be available. Currently, some of advanced vehicle maker now providing OTA service, but in the future, the OTA will be the mainstream. Then this 5 mega trend transform the vehicle industry like this. This is the stock value of the company. You can see that I mentioned the Toyota and GM, and the Volkswagen is a major in market share, but in the stock value, the Tesla is a top. Even though Tesla is not listed in the market share, top market share, or the the company in the revenue, in the stock value, this evaluate is highest than other big company. And also here is a mobility market instead of the manufacturer market. The Uber and Lyft is a mobility service company. The stock value of this company is even higher than the big giant of the vehicle manufacturer. It shows there are already the revolution. The automotive industry are under the revolutions. Okay, then I talk about the level of automation. Then in the autonomous vehicle, we can classify in the 6 stage of automation from level 0 to level 5. Level 0 is no automations. Level 1 is for some driver assistance. The level 2 is supporting the occasional self-driving. For driving the vehicle, the driver need to pay attention. It's for monitoring the environment using the driver's eye, and also he or she need to using the hand. But for in the level 2, the driver is allowed to temporarily hand off or eye off. Then we call this kind of system is ADAS system. ADAS means Advanced Driver Assistance System. But in level 3 is for limited self-driving. What the limited means? It's for self-driving. We classify the vehicle is autonomous vehicle. Its level is higher than the level 3. Then to level 3 is for driver is allowed to hand off, eye off during whole the driving time. But there is for the limitation. Even though the vehicle cannot handle some situation, then driver must take over the vehicle's control. Then the driver must handle after that. That I will talk about in the later slide for details of this one. But anyway, for level 3, driver must sitting on the driver's seat, and the driver must return to the driving task. If the AV system asking driver to return to the driving task. And for level 4 is a full self-driving under certain condition. Driver still driver is mandatory on the driving seat, but the driver never mind. It's free from all the task. Therefore, we call this stage is for hand off and mind off, never minding the driving task. The driver even can sleep in the driver's seat. And the level 5 is for final stage is for full self-driving under all condition. That even though the vehicle can driving without any drivers, any passengers, any occupant in the driver. You can see the Hollywood movie. The vehicles is a very intelligent vehicle moving itself without the humans the control. I think that this kind of is a final stage. Is the level 5 stage. Then we are now in 2020 to 2021. Then we are now in the from transition from level 2 to level 3, and the level 5 vehicle will be appear in after 2025. It's about 5 years later. Okay, then let's talk about the challenge for the autonomous vehicle. There are 3 main category of challenging issue. One is for the technology, the other is for the social acceptance. Also, the big challenging issue is for the business model. The technology is for we must meet the basic requirement of performance of level from level 3 to level 5, and also we guarantee the functional safety also. Also, there is a for issue of cyber security also. That this kind of thing is related to the technical the issue, and the social acceptance is there is a comfort issue of comfort, and the vehicle we are we are used to human driving vehicles, but if the changing in the machine driving or self-driving the vehicle, we may feel the uncomfortable. It may cause for a social issue. A person do not like to take the self-driving vehicle because it feel uncomfortable in this kind of vehicle. That is for one issue, and maybe the autonomous vehicle may causing the congestion in the city, or the driving behavior is if it's quite different from the human driving car, it may cause for the social issue. And for business model, there will be some change in vehicle ownership. Then nobody need to own their private car, because if the old vehicle now become the autonomous, we don't need to purchase one. We don't need to take care about our personal vehicle. Then all the mobilities becomes mobility as a service. Then there are big change in the vehicle industry. Currently, the vehicle manufacturer produce vehicle, then each person purchase this one, and he is the owner also driver. But in the future, the business model, that nobody need to own the vehicles. They only need to using the service also. Then we expect there are big change in the business model in the transportation society, also in the vehicle industry. Also, let's look at the social acceptance first. This is for the survey of the question is a survey on the two questions. The first question is, would you ride a driverless car? The answer is the marked by the blue, and the second question is, would you kid ride driverless? This is marked by the green. Then in the average, in the worldwide, only the 57% of in the worldwide is agreed to using the driverless car. But if you see the statistics of each country, the Brazil and the India is a very high. There's a positive ratios, but for the more the industrialized the company, the country, and also the big the automotive industrialized the country like German and Japan, only for Japan less than 30% say yes to willing to take driverless, or willing to let the kid ride the driverless. Only the German is about only 30%. It means still in worldwide there is no the global the consensus for accepting the driverless cars. Yeah, then I'd like to talk about the opportunity of the autonomous vehicle. Actually, the AV is leading a new industry. So for intelligent vehicle industry, then it causes a new create new industry and a new market in the intelligent one and the connected one, and there are a lot of new the research issue related to the intelligent the vehicles, and also it's a connected one, and it's also impact on lifestyle, new business, and the economy. Let's look at first the opportunity for the autonomous vehicles. Then it's for autonomous vehicle, it becomes the connected intelligent car. So connected means it's connected to the internet, or it's connected to the vehicle to everything. Then it's there will be for the new the business in the traffic safety, and there is a new business for the remote care, the maintenance and diagnosis, and the software update for the this kind of vehicles. And there is for new business for the mobile office. The vehicle, the inside of the vehicles will be actually it be a good the office for the occupant. And also there is a big change in the entertainment for audio, video, and game, enjoying this kind of thing inside the vehicle during the autonomous driving. And also there are the driverless car and the valet parking service, and also the autonomous taxi will revolutionize the private and public transportation. And also there will be a big change in the car sharing service. Currently, the carpool or car sharing service is not popular because it's not easy to the access to the vehicle. But if the whole vehicle is connected and intelligent, it's moving and autonomous, you can implement the car sharing service so very easily. There is a big changing in this one. Also, there is a big changing in the traffic efficiencies. There is optimization in the route. We may take the optimum the path for from source to destination, and also there's the number of traffic will be reduced. Then it's cause also the traffic efficiency also. There are big opportunity for the business and also in the public service. Also, the benefit of autonomous vehicle, there is it cause improve of safety. As you can see, the more than 90% of all accidents are caused by the human errors. Then the number of the traffic fatality is for usually is in the advanced country is 1 million about 100 person is killed by the traffic accident in most of our advanced country. Like the Korea is 1 million per 100 per 1 million in Korea, and the United States every year 30,000 deaths per year in United States. You may know that the population of the United States is 300 million, but it's almost the same. It's 100 per 1 million. That's the cause of this kind of traffic accident is caused by the human error. If you adapting the autonomous vehicle, we drastically reduce the traffic accident, and also the environmentally we can reduce the emission by using the driverless car. Also, there is for the productability is quite increased because during the currently during the driving, we cannot do anything. Just we must concentrating on the driving task. But if you are sitting on the autonomous vehicle during 1 hour or 2 hours per every day, you can free from the driving task. You can do some the other task. Then it can increase your productivity. Also, it provide a great freedom to the elderly or some the person disabled persons. Also, there is for the prior study showing the impact of autonomous vehicle in the new business and the new lifestyle. This is project called the Project Boston 2030. This is for the modeling Boston City, the autonomous vehicles. This the phase 1 model of the Boston City in year 2030. Then there's the modality of the Boston City. We assuming the modality shift to this phase. The 11% of traditional private car, 50% of the public transit, 22% of shared driving taxi, 4% of self-driving taxi, 11% of self-driving private car, 2% of traditional taxi. If you assume this kind of the new modality, then the impact to the Boston City is for listed here. The number of vehicles reduced to 11%. The distance traveled for each vehicle is increased 13%. Average travel speed increased 15%. Average travel time is reduced 11%. The emission is reduced. So amazingly, is for 42%, and for parking space in Boston is reduced to the demand is reduced to 16%. But in the second phase, the scenario, assuming the scenario of a robot transport revolution, then we assume that there's no private owned vehicles. There's 34% of the public transit, 14% of shared self-driving taxi, 24% of self-driving taxi, and 28% self-driving minibus. Then you can see the impact caused by this kind of modality shift. The number of vehicles reduced 28%. The vehicle distance traveled, the 6% increase. Average travel speed increased 30%. Average travel time reduced 30%. Emission reduced to 66%. The parking space is also very amazing. The result, parking space needed to in Boston City is reduced to about 50%. You can see you can expect how much the budget required to build 50% of the parking space in Boston City. I said huge amount of budget required. Also for increase the travel speed about 30%. It's also very huge amount of the budget required. But only the changing the mobility by adapting the fully autonomous vehicle to Boston City without any of additional budget, you can expect there are a lot of positive effect in environment, energy, and travel time, and also the parking space. Also, yes. Then I'd like to introduce the key AV technologies developed by the Yonsei Seamless Transportation Lab. Then I'd like to introduce the five the technology the developed it or the under the developing by lab. One is for end-to-end steering control, and the second one is localization and mapping technology, and the third one is driving comfort of autonomous vehicle, and third one is in-cabin monitoring, and the last one is the dynamic driving task and the irregular situations. Actually, the Seamless Transportation Lab start to develop the autonomous vehicle from 2010, and then this is the first autonomous vehicle. It's developed in 2011. It adapts the differential GPS and radar and camera, and using the lab view system for controller, and we use the PC, and we using the tracking pre-planned path. Then it's a very early stage of autonomous vehicle, and the second wave is we got the autonomous vehicle the license from government. In Korea, we have the license system, doing some kind of the real test under the supervisor. We got the driver license for the autonomous vehicle. This is actually the first licensed autonomous vehicle from the government in my lab. Using the LiDAR camera and radar technology, and we using the NVIDIA GPU drive PX2 system for the controller. Then we adapt the end-to-end steering control. The end-to-end steering control is the learning-based, the deep learning-based the control system. Then in 2019. We got the license. We developed the third autonomous vehicle using the camera and using the LiDAR and radar, and using we replacing the NVIDIA Drive PX2 to the Linux PC, and we adapting the neural processing unit. Then we developing the learning-based control system, and for the localization and the mapping system for the lateral and longitudinal controls. Yeah, then I'd like to introduce what is the end-to-end the steering control. Then for end-to-end steering control is for deep neural network-based autonomous the vehicle control system. The aiming is aimed to develop human-like the driving. You know that the humans we learn driving, and we adapt some kind of changing of the environment and the situation. But sometimes we make some mistake. Then usually there is a basic self-driving loop. One is for from the sensing and perception, and there's a decision loop. There's a control loop. We call it a self-driving loop. The perception based on the perception is decision and the control. There's a looping like this one. But actually, the human. So the human-like driving is a little bit different from this one. The human, in your eye, you can see, and we never calculate the curvature of each lane or curvature of each path. We just learn. We are experienced in this speed, in this curvature, how the driver can control the steering. Then it's for the learning based. Then for the human-like driving, we must decouple the step-by-step architecture. Perception, decision, control. There's a perception, there's a algorithm. The decision, there's for some many differential equation for deciding some kind of actions, and there is for actual control. But for human driving, there is a decoupling of this one. There is the camera input. There is for the convolutional neural net. It's learned, and then there is for the controlling steering by drive by wire. This kind of system is adapted in the NVIDIA's BB8, the autonomous vehicle in 1960s. But this NVIDIA is they adapt the DAPT, the autonomous vehicle system. DAPT is actually the architecture of this one. This DAPT means DALPA autonomous vehicle. Is the version 2 autonomous vehicles. Basically, the first autonomous vehicle adapt the DAPT the architecture. There is the front camera, then there is a text image, then there is for the DAPT the neural network. Then we slightly modifying the DAPT. Then we named it DAPT Sky, and then there is for the actual control by steering by wire system. Then the basic architecture is very simple, like this one. So camera, then the neural network, and then this for direct control through the CAN network of vehicles. Then for the training of this kind of system, in the pre-training phase, we apply the supervised learning by the simulation. The pre-scan is a very well-known the vehicle simulator. And then we take and the recording steering field angles and the matching to the video input. The camera record the image, and then we take recording the steering angles. Then we train the DAPT Sky the network by this kind of a supervised way. There is an error, the back propagate to the DAPT Sky deep neural network. But we modify after this the pre-training. We add on the second the training for we call this a reinforced closed loop feedback for post training. This is for first training, and then we put the preview driver model, and then actually from the image and the image from the input image drive DAPT Sky is output the computed the steering angle, and there is for the driver preview model. There's the desired steering angle. There's a back propagation for the training drive network. There's another the feedback to the vehicle, the changing the vehicle state and the training the driver's preview model. Let's look at the simulation environment and the test environment. The details of the experimental result will be shown by the Dr. Mishra after this lecture. That here is for the simulation environment. During the training, the vehicle moves in these directions. So counterclockwise, but in test drive, the vehicle moving in the opposite direction. That's why in the we using the same route. Only we using the one route, but we can provide the different environment for vehicle during training and during test. Let's look at the result. This is for the only for DAPT is the pre-training result. This is for DAPT Sky, our reinforced the second training. In we facing the very steep curve. This is a departure the lane, but DAPT Sky still keep the lanes is very well. Yeah, let's look at the difference in the steering field angle. Is for the green one is for pre-training only. That is for the red one is ground truth. Is for the by the expert human driver. This blue one is for we apply the post-training. The post-training is very well following and the ground truth in the CPs in the curve. Only the previous pre-training and the vehicle is departure the lane, but the post-training, the vehicle with the post-training is still the following the ground truth very well, and this shows for the error of ground truth and the post-training. The data from post-training here is at this point you can find that the error is big. Then is departure the lane in the previous. Then only the pre-training is applied. Okay, the second issue is if the front vehicle is very close to the ego vehicles, then it's the ego vehicles camera cannot observe the full the lanes. Then this is a fully observable and a partially observable case. If there's no the front vehicles, if there's the front vehicle is very close to the ego vehicle, is for distance is only the 8 meters. This is for about 10 meters. You can see if the front vehicle is close to the ego vehicle, you cannot see the lane curve. Only you can see the partial information of the lane curve. In this case, this shows for the simulation result. This is for the 8 meters is for 10 meter distance. This is for ground truth. Then is for 8 meter in the only the 8 meter distance. The lane is a departure after only for the about 300 to 400 the frame number, but for the 10 meter difference, it can follow the ground truth of the steering, the control values. That it means even the some part of a lane information is invisible by the obstacle in front vehicle. If there's the margin of 10 meters, the distance of 10 meters, this kind of end-to-end steering control can work properly for the autonomous vehicle steering controls. Okay, let's look at the second issue for the dynamic localization using vision and map matching. For the aim, our concept is for the human-like navigation for autonomous vehicle. When you want to go your destination, currently you press or you call your destination point. Then from the starting point, there will be the planning of a route. Then the navigator guide you to the how to arrive your destination. In our approach is very similar to this kind of approach. Our approach is for the autonomous vehicles, the localizing dynamically its location without very accurate DGPS. And without DGPS, we use visual map matching, like the human driver. We only see the environment by eyes. Then we know where I am, where the vehicle's position and the vehicle's heading. We call this the visual map matching, and then we can control by end-to-end control. Therefore, we have end-to-end control. Then the second thing for human-like the autonomous driving, we need visual map matchings. We extend the system architecture for the AV controller. There is a camera, there is a GPS and the IMU sensor. There is a LiDAR for the sensing and detecting the environment and the position on the map. We need the high definition map. Then we have a for perception, the function for the object detection, traffic light detection, rain detection, and other, and for localization. And we are the planning, and we control the lateral for the steering, control for lane keeping or lane changing, for the longitudinal control for the acceleration and for the braking the vehicles. Okay, for this purpose, we develop this kind of network. It's a tracking position and the heading angle on the high definition maps. This is for the map. This is for this the red dot is a current position on the map, and the angle is for the heading of these vehicles. And this is the camera, and this from the camera input we extract the lane recognition and with the segmentation using the CMS network. One is for the visual understanding. The other is for the matching with the visual information to the map. We can accurately positioning the vehicles, the current position, and for heading angles of vehicles. This is for the multi-lane the case, so for the real-time tracking. This red one is for the position by GPS. You know that GPS is about 10 meters, about 10 to 15 meters the error. But that's why the GPS only guiding the rough location of vehicle is with about 50-meter error. Based on that, we roughly estimate the position of vehicles, and then by this kind of map matching, the visual map matching, we adjust the location and the heading angle. The CMS network, the output, the real-time position and the heading angles. Based on that, this for the overall architecture of our third autonomous vehicle. There is for LiDAR, sensing the obstacles detection in the ROI. ROI is means the region of interest. You are planning to driving this the trajectory, then you have a region of interest like this one. You detect the obstacles in the ROI region, and then from the map you plan the desired path on the map. Based on your destination. It's like your navigation guiding you to the path to your destination. It's very similar. Then here is for your current location. Then is for your the desired path on the map. And then from the map, and the camera input, and this one, this for convolutional neural network, the controlling the steering. Based on that, you are controlling the velocity. Then this for the lateral and longitudinal is by controlled by the deep neural networks. Okay, here is for some demonstration of the vehicle. This is for lane change. You can see here is for the you can see the in-cabin, the camera. Here is the map. The vehicles moving in this direction. This is for the image from the camera. That is for the detect the rain. And this is for the left turn case. This is for the left turn case. This is for right turn case. You can turn even though in the intersection there is no lane mark, but you estimate your position in the map. You can estimate your position accurately on the map. That's why you can the control, even though the occasionally there is any the lane marking on the input image. You can safely control for turn left, turn right, or for lane changing maneuvers. Okay, the next issue is for driving comfort of the autonomous vehicle. I hope that you may have some kind of the basic knowledge for the lateral and longitudinal acceleration. This is for x-axis is for the lateral acceleration. This is for longitudinal acceleration. Longitudinal acceleration actually is for the when you drive the vehicle is the accelerating or braking. This is for the actual acceleration of for accelerate for plus the longitudinal acceleration means is for the acceleration. Then the minus the acceleration means for the acceleration of for braking. Then for younger driver, the aggressive driver, so enjoying the aggressive driving. Then it's for the quick the acceleration and the with for enjoying the sudden stop. Therefore, younger guys usually like the sports cars, but the younger guys for like to have a very the big plus the longitudinal acceleration and the minus longitudinal acceleration. Then what is the lateral acceleration? When you make the turns, the lateral acceleration means is for the acceleration caused by the turnings in the curve. Then it means the big lateral acceleration means with the driver enjoy the turn in without reducing the vehicle speed. That's why each of a driver has one's occupant preference metric in this curve. Why we call the occupant preference metrics? Because in the autonomous vehicle, there's no driver. The passenger in the vehicle is only for the occupant. But when he or she the driving he or her vehicles, they have the preference metric in this. You can marking the preference metric in some area in this matrix. Okay, then based on the occupant preference matrix, the occupant select once the preference metric based on the preference selected, we can optimize the motion planning and the control. Then it's optimized planning. Then it's for the lateral longitudinal control based on the criterion of lateral and longitudinal the acceleration. Then you can sensing the vehicle the status. Then we got the vehicle status from the sensor. We based on this criterion, we control the motions. Like this is for kind of autonomous vehicle route. This is for the preference matrix. Here is for the experimental on real load test. We are making this kind of the real load test. This trajectory. There is for steep the corner. We make a right turn in each corner. Then we are selecting the occupant preference metric like this the criterion. Then the autonomous vehicle is following. It's not exceeding the criterion of the preference. You can show the acceleration of the vehicle. This is under this criteria. Okay, the next topic is for the dynamic driving task. What is a dynamic driving task? When the driver driving the vehicle, the driver is for actually doing it's the detecting the object and the event and the responding. We call during the driving, the driver doing the OEDR task, the object and the event detection and response. This kind of the OEDR process, including this OEDR process, we call is for the dynamic driving task. Then for doing for this the OEDR, if there is for some the pedestrian on the street, the driver must detect this pedestrian, and then the driver decide whether we stop or we bypass this pedestrian. This is for the response of a driver. But this is for normal situation. If there is for the operating domain is for exceeding some the limit of the driver's the capability, we must doing the fallback system for the guaranteeing the safety. Then let's look at more details of the dynamic driving task and the self-driving process. In the driving task, we can classify the task is for the three functions. One is for the strategic function, the other is for tactical function, and also is for operational function. The strategic function is for we choosing for destination, and based on the destination we are planning. For like we may take a highway or we take a local way. It's for we are doing the based on the toll fee or the traffic jam, expected traffic jam. We choose the path for arriving destination. This is for the strategic function, and for during the driving, we are sensing environment, and we are doing the OEDR. OEDR is for object and event detection and response. I explained in the previous slide. And then there is for the operational domains. We call this for the ODD. The ODD means each driver can driving in the environment. For example, most of you are the Indian. The Indian is a very warm weather. Can you driving in the icy road with 100 km/h? You can drive in the under the snow. You can drive your vehicle in 100 km/h. I think you never experiencing this kind of snowing the highway condition. maybe it's out of your the operational domain. It's your the domain capability. That is the concept of your the ODD. There is for this the system, for self-driving system. There is for the operational domain, preset operational domain. It means the vehicles can drive autonomously in this domain. If the environment exceeds this domain, it cannot handle. It's out of control. That is the concept of the ODD. Under the ODD, there is for the OEDR. That is for tactical functions. They're doing the OEDR, the performance. Then based on the OEDR, we control lateral and longitudinal control. As a consequence of this control, there is a changing in vehicle state. There is a feedback, and also there is a sensing environment for the rain and the mapping, and for the other the raining one. There is for other one, the night or the windy or foggy, and there are need to sensing the the environment. That is basically the dynamic driving task of the autonomous vehicle. Then what is for the level 3 and level 4? It's back to the beginning of this lecture. For the level 3, I told you that it's for the self. Quickly back to the slide. For maybe I need to remind you for this one. Can there be something wrong in sharing? Okay, I do.
Hello, sir. Hello, sir.
Yeah. Okay. Okay. Now we share. Okay, sharing the slide again. Yeah. Here is for the level 3 is a limited self-driving. It means it's the self-drive. Even though it's a self-driving vehicle, there is not full self-driving. There is a full limitation. Then what? Then I try to explain what is the level 3, level 4, and level 5. What is the difference of this one? Then for level 3 is for there is a limited self-driving, and is a full self-driving on the condition. That is a full self-driving on the all condition. Then I'd like to explain what is the difference in the dynamic driving task in these vehicles. Okay, this is for this axis means the driving time. Then this ADS means the autonomous driving system. Then it's performing the DDT. Then there is for approaching the ODD exit environment. Then the level 3 vehicles, the ADS system, the alert the driver. There is in front of this vehicle. There is for the ODD exit environment. Please wake up. But if there is no response to the passenger, then this is for the DDT fallback system. Then the ADS system must perform the minimum risk condition. Must control the vehicle in the minimum risk condition. If the driver wake up or back to the driving task, then driver performs the DDT task. Then exit the ODD exit condition. Then this is for level 3 autonomous vehicles, the loop. For level 4, it's for full self-driving under certain condition. Then if there is for ODD exit environment in front, the vehicle do not the alert driver. Then vehicle automatically move to the DDT fallback system. Then it control the vehicle in the minimum risk condition. For level 5 vehicles, what's wrong? There's no ODD exit condition. It full self-driving. It must driving all conditions. There is no ODD exit environment. You can driving anyway, any condition, anytime. That is for big difference in the level 3 to level 5 autonomous the vehicle the stage. Then for the artificial intelligence up to the level 3 autonomous vehicles, usually you are very familiar with for recognition and detection of environment. There's a lot of the vision for detecting something, and there's for the image segmentation. There's for a kind of the attention loop for understanding of a prediction of some environment. This kind of a commodity deep neural net for artificial intelligence is for autonomous vehicle up to the level 3. Then for the above the level 3 vehicles, we need more intelligence one. This for what kind of a situation we will face. This is for the road. The green node is the vehicle is taking this green node. This side is the parallel node. You are now the vehicle driving, following this lane, but you can change this lane. This is for same direction, but this is the opposite lane. You cannot move to this lane. But here, this is a one way. You can go this way, but you cannot go this way. This is for a kind of safety zone. It is for the part of street, but you cannot enter this area. This case is the most difficult case. This is for the urban street without the central lane. Then the human driver, you arbitrarily assume that you have the virtual center line. Then you driving in this the right side. I'm sorry, the India you are driving in the opposite way. Maybe you arbitrarily making your the virtual center line that you take this way. This is for the normal the autonomous vehicle for level 3. This case is for the beyond the ODD operational domain. For autonomous vehicle above the level 3, we must have this kind of the artificial intelligence technology. Yeah. Then for the other examples for irregular situation, for ODD case for the level 3 autonomous vehicles. When you're driving, you can see this kind of beautiful lady, but this is a picture, not the real human. If in the street, if there is for advertising the wall or painting, most of our current deep neural network is recognizing as a human, but it's not a real human. It's the picture or photograph. But the human easily recognize, it's not a real human, it's the picture. But this is also for simple case, for the ODD case. Then the other case, this kind of thing. This is for policemen. This is for traffic signal. The traffic signal is the red light. The traffic signal says it's a red light. But the policeman guiding, controlling by hand gesture, you can go. But the human driver, we easily understand that. The policeman has a higher prior ability to control the traffic. Then we must follow the policeman's control. But in the level 3 vehicle, it's for detecting the signal, but do not understanding the motion, the hand gesture of a policeman. Even the system cannot recognize where he is a policeman or not. Then this kind of thing is a very the difficult case for the ODD of level 3. And then this kind of thing is also very dangerous situation. You can driving, there is the pothole, you can pass over the pothole. If you find this kind of the blocks, you must stop. But in this case, there's something. There is a paper or is the vinyl. You can just ignore this one. But the current autonomous vehicle cannot recognize this kind of difference. It can only detect there is some obstacle, but you must recognize the property of obstacle. But you must recognize this one only within 100 milliseconds because you are driving more than 100 kilometers per hour in highway. If you need some time to deciding for several seconds, already you passed this station. Already there are something happens for the accident or something wrong. Therefore, this is for you must only have 100 milliseconds for you recognize the material properties on the road. Although there are many very difficult the environment and the irregular the traffic situation. There is under construction. There is this road is the broken. Then you must go. You must go in this lane, but it's not allowed. Normally, it's not allowed to driving. But in this situation, you must following this road in many different cases, or even you must communicate with the bicycle rider by hand gesture. Then your vehicle must understanding the hand gesture of the bicycle rider or the driver in other vehicles. This kind of thing is actually we need to develop the artificial intelligence system beyond for the level 3 autonomous vehicles. Okay, the last topic is for in-cabin the monitoring system. In the fully autonomous vehicle, there is no human driver inside the vehicle. Then essentially we need to require monitoring the inside the cabin. Because there will be the children, there will be sitting they're not fastening the seatbelt, maybe some the drinking or maybe it's for smoking the cigarette, or there may be a lot of things happening in the shared vehicles. Therefore, we need the in-cabin monitoring system. Then the first thing is we can where is the proper or optimum position of the camera in this kind of the fully autonomous vehicle. Then we may thinking about the front camera like this way. The front camera see only the front driver, in the back side driver, you can not the fully observable the passenger status, and therefore with the ceiling camera we can take the full inside of image using the single camera. Then we can detect some the object maybe causing the safety or maybe the other the important the obstacle using the knife or cigarette or there's something for luggage or the drinking. You can monitor all kinds of things in the ceiling camera. But the other important issue is for the privacy issue. If you monitor the using the camera inside the cabin, and all the real face will be recorded, will be cause for the violate the privacy the issues. That's why we need for for technology for the face anonymization. Then we developed the face anonymization technology using the virtual face and the phase shift gain. This is for real photo. This is for the target image. Actually, this for target image is not the real human face. It's for the it's a virtual human. This face is generated by the artificial intelligence using the virtual face. We are applying the face anonymization technology using the virtual face. Then this is for the Asian woman, young woman. This is for the Asian man. That is the Western woman. That is the Western man. We apply this for the virtual face to this kind of original pictures. You can see the originally this is the Western man, but we apply the Eastern lady. It's look like you can see it's looking very strange. But if we apply the Western man to the original image, you can generate a very looking not so bad, looking good the facial image, and then we can keep a kind of facial the emotional expression in the driver. That's why you can say that using the similar the target image for the man, woman, age, and the Western style, Eastern style, then by combining, then mixing the target image to the original image, we can generate for face anonymized the image. Then we can record this image. Then we can free from the privacy legal issue in the in-cabin monitoring systems. Okay, this is for the last slide. I'd like to conclude the today's lectures. I outlook the current status and the challenge and opportunity of autonomous vehicles. And we can say that the vehicle industry now facing a destructive revolution. The autonomous industry will be the last industry of the destructive transformation. Already many of the traditional industry like the phones, the home appliance, the media, now is under the transform or is already transformed. But vehicle is still there is for the major stream in current status is for the traditional one. But in the near future, in the next decade, the vehicle industry will facing the destructive revolution. I talk about the mega trend of destructive revolutions. And the autonomous will changing the lifestyle as well as for the ICT industry. Actually, the vehicle is for different from ICT industry, but after by the destructive revolution, the vehicle industry will be part of ICT industry. That's why the global the IT company like the Apples and Google they try to move to the vehicle industry because vehicle industry now is a part of ICT industry, and the autonomous vehicle providing actually the next ICT platform, and the whole of this is the status and the revolution and the platform, the artificial intelligence is the key enable technology. That's all. Today's my lecture. Thank you for your attention. Thank you very much.
Thank you so much, Professor. Uh, shall we start, Ashutosh? Mr. Ji?
Yes,
Dr.
sir. Sure. Sure, sir. Can you see the slides?
I can see your slides, yes.
Okay. Should I start?
Yeah, let's make it for half an hour, right? So maybe at 11:30 we'll start a short panel discussion, then some other formalities. So by 12 o'clock you should be able to somehow.
I will try to finish as soon as possible.
No, don't go as soon as possible. We'll go by. So, make it by 11:30 or so. Huh?
Okay.
Okay. Please go ahead.
So the today's talk is about AI for autonomous vehicles, and Professor Kim has already told you people in much detail. So I would like to start the presentation from the introduction of my lab. So in this presentation, we will see the research ramifications we have in our lab. So first we will see the end-to-end steering control, and then I would like to share some demonstration which we have demonstrated at Seoul Smart Mobility Expo, and then we will go for the smartphone app-based sharing service in autonomous vehicles, which we have developed with the SKT company and Yonsei University. And then I would like to showcase the development of 5G network-based intelligent management server platform for commercial vehicles. It was the project given by Acetel, which is one of the localization-based company. And it was for the mobile CCTV. We will see in further slides. And then I would like to go through with the details of irregular situation autonomous vehicles on which I am currently working on. So this is the brief introduction of our lab, which Professor has already told you people. So we have right now 3 autonomous vehicles. The first vehicle was in 2012, which was equipped with the differential GPS system, LiDAR, camera, LabVIEW, PC, and tracking pre-planned path. The second vehicle was purchased in 2015, which is equipped with the camera, LiDAR, radar, and it has NVIDIA general processing unit, graphical processing unit, GPU PX2, and it has end-to-end steering for learning-based modules. And then our third vehicle was purchased in 2018, which is also equipped with the camera, LiDAR, radar, and it has Linux PC and the neural processing unit on which we can train and inference different kind of models we are going through. And it is based on the learning-based control as well. So the vehicles are equipped with different sensors. The main sensors we can talk about the different equipments like the NVIDIA Drive PX2. It is an open AI car computing platform which combines the deep learning sensor fusion and the surrounding vision. And we have the IBO LUX 4 level scanner and 8 level scanner, which is the LiDAR sensor which supports the object classification and tracking. And it allows the environment in field view of 110 degrees. And then we have the Navital GPS, which is a high precision GPS with the original equipment manufacturer, and it supports different kind of GPS techniques. And the autonomous vehicle is equipped with the cameras, which supports the advanced driver assistance system, and it supports the connectivity with NVIDIA tools as well. Then we have IMU, which is for the inertial sensor. It has a set of 3 gyroscopes, 3 accelerometers, 3 magnetometers, and temperature sensors. And it can compute precisely 3D orientation of the vehicle. Then we have the Delphi radar 2.5, which has wide field view and the mid-range, which can cover the long and mid-range coverage. So I would like to share the video. Can you see the video? Hello, Professor. Hello. Yeah. Hello.
No, sir. Right now,
Yeah.
we can't see.
Uh, I'm sharing the video. Is it visible?
So not yet.
Okay.
It's not played actually.
Yeah, your screen is displayed, but the video has not opened yet.
Let me see.
I think it's not played in your system itself, right?
No. In my system, it is playing.
But just we can see your. Okay.
You are in the full screen mode. If you exit full screen mode, is broken.
Okay.
You must reshare.
Again.
Okay.
So you did not share your whole screen, or you might have shared one window.
I have shared whole screen, but video is not running.
Restart.
So which particular video player you are using right now?
The Microsoft.
Big bug. Micro bug. You can share instead of. Now it's okay?
Yeah, we can see your slides.
Okay.
Yes.
Yeah, and then you share this screen instead of.
But video is not playing actually.
Let's play it.
It's okay.
Okay. So right now, is it visible to you people, the video?
Yeah, we can see it. Yes.
Okay. So in this video, as I already explained, that we have 3 autonomous vehicles. So this video is portraying the demonstration which was captured at one city, and the lap was around 2.4 kilometers, and the vehicle was capable to move with the 30 kilometer per hour speed. You can see here the descriptions are there, and total area was 24 kilometer covered. So this is the lap. In your video screen you can see the lap covered, which is at the Sehong city at Korea. This is the lap. It is around 2.4 kilometer, and total distance covered was around 24 kilometer. And this was the vehicle, which is equipped with different sensor we have just talked about. So this is the real-time video captured on that same lap. This is the video showing from the another vehicle, and this is the main autonomous vehicle. Then later on we will see the this is the black box video which was captured through the vehicle. This is the original video frames we are capturing. These are the logs, and here we can see there is one window for black and white binary video. This is the path we are going on, because here in Korea it is the left driving track, and this is the screen where we can see and sense the coming vehicles and obstacles, etc. So as we can see that we are moving, and there is one bus which is coming, so we can see in that video it will be detected. Yeah, you can see. It stops. Okay. So here we can see the bus is there, which is captured with the bounding boxes. And this is the captured green bus and other vehicles we can see. Yeah, again there is green box. So this was the brief description of our lab. Then we will go with the next slide for the end-to-end steering control. So this was published in a paper in the IV Intelligent Vehicle Symposium in 2018. And the concept is related to the DARPA autonomous vehicle DAPT2 system. So basically the DAPT2 system has one NVIDIA driver PX2 which supports different camera like left camera, center camera and right camera, and it has a CAN bus through which we can see the steering wheel angle, and we can control our vehicle, and it has the connectivity with the external solid drive through which we can put our database for inference and training purposes. So the concept is related to as explained by the professor in previous session. There is the model, CNN model, which can see the actual adjustment and shift of the steering wheel, and after capturing the screen, the video and image visual sensors from the different camera sensors we have, we can predict what should be the exact steering for our vehicle, and if there will be some error, then through the back propagation we can adjust that error so that we can go for the exact steering angle we require. And this is the basic concept of our DAPT2 system, which was from the NVIDIA, but we have proposed DAPT2 with two training phases: pre-training and post-training. Post-training is the reinforced training. The pre-training was actually from the pre-scan, which is a simulator which only simulates the virtual scenario situation, but we have adopted the pre-scan model and we have retrained that model with our own network. That network was this. It has 5 convolution layers, as we can see. Convolution layer 1, 2, 3, 4 and 5, and it has 3 normalization layers, batch normalization, and then it has 2 fully connected flat layers. Finally, at the output we are able to predict the steering wheel angle. So the whole system works like there will be the visual sensor through which we will capture the video images and the real-time frames, and then our DAPT2 model will predict the value of the steering angle, and then accordingly the vehicle can move, as we have seen in our previous demonstration. So we have captured the input at the frame size of 160 cross 90 in RGB frame. So this is the track we have chosen for testing and training. Already professor has told you people that the training direction was in counterclockwise and testing was in the clockwise. It was just to preserve that the training and testing inputs are totally different. They are not same for the model, so we can avoid any kind of overfitting or cramming situations. And we have different like curved road and straight road kind of scenarios in our lab chosen, and this lab is actually at the Yonsei University. So we can see the scenario is like there will be the ego vehicle, which is the autonomous vehicle on which we have implemented this DAPT2 system, and there will be some front vehicle. So there might be 2 scenarios, that in the front there is no vehicle, like we can see in figure B, and if there is a vehicle, so what is the minimum distance through which we can estimate the exact angle. So we have chosen the minimum distance at 8 meter and 10 meter, and we will see the results in future slides. So basically there are two kind of scenario: the fully observable scenario and the partially observable scenario. So these are the experimental route which we have seen, and these are the results. So we can see that the pre-training model, that is from the pre-scan, it has problem while there is some sharp turn or something. It took the lane departure if there is some sharp turn, so it was not able to turn at the it was not able to predict the steering angle at the sharp turns. But the post training model was crisply identified the steering wheel angle, and it followed the track. So, and again, if there was scenario for the fully observable and partially observable, for fully observable we can see the pre-training and the post-training was applied, and the pre-training was already taken the lane departure after a few frames, but the through the post-training model we have again found the same track. But in case of the partially observable circumstances, for 8 meter there was some lane departure, but for 10 meter we have easily gone through in both cases. So in this way we have developed our own end-to-end steering control, which was able to follow the exact steering wheel angle. These are the videos. So this is the track we have followed. It is the inside the Yonsei campus. See, the vehicle has good steering wheel prediction, so it turns. Now there is the parking place where the vehicle will again take the turn and safely park. This is the position of parking where vehicle will park itself. This is the parking position, and then again it will retrace the lap after a few times. Again there is turning, and successfully it turns. So through this demonstration we have seen the vehicle was able to predict the steering control at the sharp turning as well, and it was able to park itself at the desired location. Again it turns. and retrace the path. Yeah. In the next video, we can see the valet parking at the ground level. So it is the automatic parking scenario. See, safely the vehicle was able to park itself at the underground basement. These are the simulation results which you have already seen in previous session. So here the first screen is showing the steering wheel control for the pre-driver mode, and this is our proposed CNN model through which the DAPT sky system was developed to predict the angle. So here we can see the pink line is showing our own model, and the yellow line is showing the previously trained model. There is sharp turn and there is lane departure. The vehicle in the pre-trained model was not able, it was failed to take the turn, but in our own trained model in the simulated environment, the vehicle was able to safely took the decision. So in the real scenario and in the simulated domain, the model was able to predict the steering wheel angle correctly. And again, there is a test. Previous video was at the lesser speed, and for the faster speed, this video will show. This is the map of the lab. You can see at the bump, the vehicle has some jerk. See, there is a turn, so it takes right turn safely. And then maintain the lane. Yeah, there is a left turn. So it took the left turn safely and then maintained the lane. Again, it was just because U-turn was not trained in our model, so it was the manually taken turn. And then now vehicle is passing through the underground. It is able to follow the lane safely. So we have, as I told that we have developed the end-to-end steering control for the autonomous vehicle and demonstrated the same for the simulated environment as well as the real environment. Now in second demonstration, we will go with the Smart Mobility Expo, where this expo was basically for the conference and exhibition and experience, and the theme was freedom for mobility, where different participants have participated from the globe, and the expo was mainly for the autonomous driving, for ground vehicle, for urban air mobility, and for the personal vehicle. So the expo was related to the autonomous bus shuttle, the drone taxis, and the personal vehicles as well. and it was having delivery bot as well. This is the delivery bot, this is the minibus shuttle, and these are the lab for the personal mobile track. These are the drones taxis. So we have experienced these scenarios, and we have demonstrated our own vehicle in this scenario as well. And this is the slide of our own vehicle, and the video is taken from the another vehicle. So this is the autonomous our autonomous vehicle, which is third generation vehicle, and the video is captured from the another vehicle. So it is running in the autonomous driving mode. And these are the real road on the city. It is the Sangham test bed, which is developed for test bed for the autonomous driving task itself in Seoul, capital of South Korea. See here, it stops at parking. At the traffic light, because I told you here it is right. Always right turn is open because it is the left turn control here. So we can easily violate the traffic signal while we are turning towards right. As in our country, in India, we can move to the left, but yeah, here it goes because of the green signal. Because of time limit, I am just skipping and showing the main frames of the video capture. See here, you can see that it stops because you will see there is the round turn and it has to go right. It should be open, but you can see there is a pedestrian passing, so it stops here until the pedestrian goes, and then it took the turn. Otherwise, because it was the right turn, it should go directly, but the vehicle was trained to stop for the pedestrian. So the next video is the same shoot from the Ego vehicle itself. If time permits, then I will show the video, otherwise I will skip that, because it is the same video just taken from the Ego vehicle, means the autonomous vehicle itself. So should I show the video or I should go ahead?
You can show it. It's not a problem.
Okay. Is it visible? Is it visible at the screen?
Yeah, it's visible.
Yeah. So the video is taken from the autonomous vehicle itself. So here for the left turn, it stops and it predicts the decision through the traffic signal. Yeah, now you can see it predicts the left turn through the traffic signal and it took the turn. There was because of the other vehicles, it just touches the side vehicle. Now it is able to follow the lane.
Actually, there's also the free text environment in sound test bed. Actually, we can receive the whole traffic light information by air. You know, when the changing.
Yeah. Because the vehicle has to take the turn, and this green light is for the front vehicles, foregoing vehicles. So it stops. See, again for the left turn, it will take the turn correctly. Now it maintains the lane because there were the standing vehicle, but it was able to predict them and maintain the lane. Now for foregoing, it adapted according to the traffic signal. We can see it predicts the bump and take the decision. It predicts, yeah, here it is the same place. In previous video, we have seen there was one pedestrian for which the vehicle was standing. So this is about the demonstration of the autonomous vehicle which we have demonstrated at the exhibition at the Seoul Smart Mobility Expo. Now we will back to our slide. Yeah. So the next example of our research was for the smartphone based car sharing service in autonomous vehicles. So we have implemented very good concept, which is for the what three words. I will explain in future slide. It is actually to provide the precise location of the location information. So in the app we can see that there is a person asking for the car sharing vehicle, and it says that I'm standing here through the yellow dot, and through his app view it says that the taxi number, suppose 1234, is coming within 6 minutes. So the requested taxi will come to that place, but at the app view of the driver, it asks for the user that where you are asking to for me to come, is it able to stop there, because we know that we cannot stop right now at any place. So if it will search for the location, if the location which is asked by the user is available for stopping, then it will go. Otherwise it will ask for the new location. Then the user has to search the new location where the vehicle can stop. Like in the green spot we can see here there is a place to stop, and the previous yellow spot was not here, it was not able to park the vehicle because it was the main road. So the user will ask for the new location where the autonomous vehicle can stop itself. So it will be updated and then sent back to the vehicle, and according to that vehicle will come. This was the concept which we have developed in our app. So this is the conceptual diagram. Here it is the sole main control unit through which we can, the officers can monitor, can trace each and everything, and it is well connected with the cloud. So the end user will be connected to the cloud, and it will ask for some car sharing, and there will be different autonomous car shareable autonomous vehicles. They will be connected through the control unit. So when the user will ask through the cloud, the information will be processed from the control center to the nearest possible vehicle. And these vehicles are able to share the information related to the real-time information related to the traffic, related to the signal, related to the accident, or if vehicle has some problem, it is under the there is some wear and tear or some problem in the vehicle, so it will update its current scenario in real time, and it will be able to provide the information of construction, ongoing construction, or the possible location of stop at the real time through the onboard equipment, onboard unit of the vehicle to the control unit. So we have developed this smartphone app. So this is the what three word I'm talking about. This is actually creating a grid of 3x3 meter, and this grid is located in 3 words. Like for example, we can see this is the actual, the below layer is the actual map, and this is in the grid of 3x3, and there are 3 words. Like for this grid, we can see there is the word social, attending, and dive. So what it does, it actually bifurcate, it actually break the actual land in 3x3 meters, so then we can find the exact location. Suppose we are sitting somewhere, then these are the 3 meter x 3 meter grid where we can ask, we can share this location in terms of 3 word, and we can follow that 3 word to locate the precise location. So we have just implemented this 3 word concept in our vehicle, as I have just demonstrated in previous slide. So through this what 3, and this is the view of the control unit at the SOL. So here we can see they can monitor each and everything about the track, the current going situation, and inside the vehicle as well. So these are the cameras through which we can see the inside of the vehicle, outside of the vehicle, road, and there are different CCTV monitors. So at the monitoring center, one can see each and everything. And this is the another view of the vehicle control center. They can see these vehicles are on their way, and there will be 4 status. One is for booked, and then vehicle will show the on way to pick up, and another is if vehicle is already occupied, so it will say that it is in use. If vehicle is idle, so it will say the status as idle. If vehicle has some problem with the battery or it is requiring maintenance, then it will show the status as the out of service. This is the media coverage for the same.
Slide.
Yeah, professor has just demonstrated this to the YTN science channel for media coverage. So the another example is related to the development of 5G network-based intelligent management server platform for commercial vehicle. It was the project by the Acetel and Yonsei University. The Acetel is a company which provides services at the location-based service platform, bus information system, artificial intelligence, and Internet of Things. It is very big location information providing company in Korea. And it provides the black box unit, which is the onboard device unit, onboard device equipment with the most of the vehicle running either for level 2, level 3, level 4 or level 5. So we have done one project through this SATL, and the project was related, our task was related to the road condition recognition, accidental and event recognition on road, license plate recognition. This was the very interesting task because we know that sometime there is some threat or some theft related to the vehicle. Some vehicle has been theft. So if we are able to see the license plate in recognition in real time, so it will be very easy to get the surveillance. Just put the ID number of the vehicle which was theft by someone, and then on the real time basis we can monitor that these vehicles are going around on this location, so we can match the theft vehicle and we can identify that its current location is here, and we can easily go for that. So for this we have developed a CCTV in motion, which is mobile CCTV. It was based on 5G platform. So the main concept was that the onboard equipment will be enabled with the 5G technology, and it will be working as the motion CCTV in motion. So in this way we can solve many issues like the real-time traffic in each direction, the foregoing true and foregoing lanes, and we can recognize the license plate in real time. We can recognize the road and accident on the real time basis, and we can recognize the road condition. There is pothole, there is some construction going on, or what is there going on. So we have gone through this project, and the concept is like this for the commercial mobile CCTV, that there will be a consumer having the SATL mobile CCTV app, through which it will be connected through the control centers, and this control center will be connected on the 5G network, and it can communicate through the satellite GPS location, and it can see the real-time location and information and process this information to the end user. So we have showcased one case here that one person is asking through his mobile phone the location of traffic for the Daejeon city, which is a city in Korea. So this request has been processed from the app to the control unit, and then control unit asks to the taxis which are running there at the Daejeon station, at the Daejeon city, for asking them to give the real time their video at the Dejan city, so that the end user can get the real time traffic information at the Dejan city. So this information will be sent back to the control center, and from the control center end user will get the same information, and he or she will be able to monitor the real traffic scenario using this app. So in this project we have developed the deep neural network model, which will be implemented on the onboard device, and there will be the commercial vehicle black box through which we will capture the real-time video, and through this video it will be the input for the network we have trained, and then it will
Dr. Mishra,
yeah, can I
it
go?
will get if you can summarize within 8 minutes, maybe by 11:30, right?
Okay, I will try my best.
So that we
So,
can have another discussion, right?
yeah, we can see that there are potholes, there are accident, there are another road damage condition, and other. Yeah, this is the ID plate, license plate detection in real time. I was talking about. So we have done this. So you can see the video from the black box. The video images are capturing the ID plate and locating this, and the onboard device was through the rock chip. So this device was able to capture the identity license plate, ID plate in real time. So we have used the Tesseract, which is the optical character recognition engine, and we have used the OpenCV, applying the contour recognition, cropping, Gaussian blurring, and other techniques, adaptive thresholding, etc. And we have developed our own model. These are the results. So we know that the YOLO has very version of YOLO 1, 2, 3, and 4, but they are very bulky. So we have created the tiny YOLO, which can be suitable for the onboard device, and we have used the transfer learning concept. So we train and just use the inference information for the real-time capturing. These are the results which are showing that on the real time we can see the crack with the location, with the real-time information, and these are the images for that. Again, there is a road accident damage, and there is some construction or any location which shows that one-way traffic or anything is there. So we can able to see the same scenario in our real-time network, real-time trained onboard device, and it shows the location as well. So yeah, it was the project we have gone through, and we have successfully completed that. Now, this is the irregular situation in AV, which may be in the level 4 and beyond. Professor has already talked about that. There are many scenarios. So I am not going in detail. I'm just going through what we have done in our project. So as the NHTSA, the National Highway Traffic Safety Administration, says that the level 5 is a vehicle which can do the automated driving task, and the passengers will be only the occupant. They will not contribute themselves as the driver. So the problem is that there will be no driver, no in charge, only every passenger will be occupant. So who will take care of the security and safety? Because security and safety is the main issue in that case. And security is related to the vehicle itself, because the passenger can wear and tear the vehicle and provide some harm to vehicle, and security to the passenger itself, because as professor said that there will be privacy issue and other things. We will go in detail in the future slides as well. And for safety, because it is related to the safety that somebody has a hand or head outside the vehicle, so there is no in charge who will take care of that. So we have done all these things, considered these things. So mainly we will have the security and safety related to the occupant and safety related to the vehicle. So as already professor discussed, that first question is where should place the camera? What should be the proper positioning of the camera? Should we place here or there or at the center? So the best choice will be the single shot image at the center, because here we can see entire vehicle in single slot, but it has future bottlenecks we will see. So we have said that just train our model depending upon this single slot image, and it will be the best position for the AI camera, and then just use the inference of this trained model for the real-time scenario. But what I was talking about the aspect. So there will be two cases. This is the front view positioning image. Here I have just masked the faces because of the privacy issues. So here the camera was placed for the front view, and here the camera was placed for the top view. The data set we have collected was based on these scenarios, that there will be 4 positions in our cabin, and we have captured different activities like the no occupancies, the number of occupancies there varying from 1 to 4, seat, sleeping, seat belt, child seat, cell phone, drinking, eating, glass bottle, etc., cigarette, e-cigarette, tools and harmful things inside the cabin. These are few glimpses of the data we have captured, that there are occupants having their luggage, they are drinking inside the cabin, they have different harmful tools or the knife, these kind of scenario. And there are some irregular scenarios as well, that we can see somebody is wearing an apparel which has a picture itself, and there may be a picture in the rear view mirror as well. So if we are talking about the object detection, these two will also demonstrate that there are 2 more person instead of these 4 person. If we just go through the object detection, then we will see that it will detect person here and there. These are the irregular situation we will focus. So, and there are scenario related to the cigarette smoking and anything else. So as we said that there is no in charge who will take care of that, for which we require the intelligent in-cabin monitoring. So I will show you. This is the scenario I have trained on object detector. So it was able to detect the person. It was able to detect the person with the accuracy of 99.934%. For the front view images, it was also able to detect the same high accuracy. It was about 99.74%. But the scenario changes as the look angle change. If we are talking about the top view, then we can see it predicts that it is a toilet with 18%. The person is only with the 13% accuracy. There are chairs. These are the results. So only by changing the view, we can see the model was not able to predict, which was earlier showing very good result. So these are the thing we should take for the irregular situation in level 5 and beyond vehicles. So, and the next problem was related to the privacy issue, which Professor has told you. So we have done another work related to the privacy. So if we will, because we know that the vehicle will be the connected vehicle, and it has to share the real-time video through the cloud, real-time information through the cloud to the data center for further monitoring in terms of the behavior or intention of the passenger sitting inside the cabin. So we require to preserve the facial information for the personal privacy, but at the same time we have to capture the real-time monitoring as well in terms of object, in terms of emotion and intent monitoring. So if we mask the face of the person by mosaic or by blurring or something, we will lose the informative information which will be further required at the data center for further monitoring task. And if we send the real face, then there will be problem with the personal privacy. So we, for this scenario, we developed our own system which was capable of face swapping as well as face reenactment. Face swapping is just swapping two faces simultaneously so that we can have third face. As we can see here, there is a target video of Obama and there is a source face of Xi Jinping. And after swapping, we can see it is the third face which is neither belonging to Xi Jinping and nor belonging to the Obama. So we have swapped, but the problem is that we have to further monitor, further develop another event and emotion detection task. So only by swiping the face we cannot solve it, because we have to have the puppetering, we have to have the exactitude in our real-time video. So here reenactment is required. Reenactment is enactment in the same way how the target video was portraying. So we have to maintain the real emotion, real gesture of the face with the anonymized face. So we have to take care of both these tasks, swiping and reenactment. For this, we have developed the gain-based network, and we have demonstrated this in IHCI 2020. So the concept was related to develop a set of generators. The first will be for the reenactment and segmentation, in which the generator just take the segments for the head and for the hair as well, so that we can as I was talking about the reenactment, so we can easily reenact the face and hair, because as you can see that here is one celebrity from Hollywood, and this is well-known celebrity from the Bollywood. So we can see that we have taken their segmentation of facial and hair segmentation, and then we have portrayed the face swapping and reenactment. But for him, because we can see here that this face has extra space and this face was having only this position, so the mask was related to only this, and we have to swap on this face. So there will be some portion which we require to in paint, so that we can see the entire face in our segment swapped faces. So here we can see through this inpainting generator it was able to portray that, and then blending is required to maintain the environment and other background scenarios, so that we can see the exact thing. So we have implemented this concept in our proposed facial anonymized in-cabin monitoring, and these are the results. So there are many face swapping algorithms like the Navital, deepfake, and face swap gain algorithms. So these are the source images and these are the target, and these are the result for different algorithms. We can see that the FS gain was able to do this face swapping and reenactment in beautiful manner. Other than that, other algorithms are not compatible in that scenario. So this is the block diagram and the flow chart which we have developed in our own face anonymization system for the autonomous vehicle. So for the intent and occupant monitoring, we require face swapping and reenactment before the sending of the data to the data center from the vehicle. So we have applied our concept here. So these are the scenarios. These are the source faces we have chosen. These are the AI generated faces, as Professor already said, because in previous slide we have seen that there is a real person, Xi Jinping. So even after swapping, there might be problem with the identity of the source person. So to overcome that scenario, we have chosen the artificially generated source images, and there are two. Yeah, we have taken care of the look as well. We have taken care of look and gender. So we have taken care of the Eastern and Western look, and we have taken care of the gender as the male and female. So we can see the results. So for the Western look target, we have swapped the face with these source faces. Professor has already explained the scenario. We can see the base swap face was obtained when we swapped the Western looked face with the Western male. Instead, we have not got the exact result, because I told you while monitoring we require the exactitude so that we can portray the same emotion or something, because our task is to monitor for the safety and security and to preserve the privacy. Here the look was changed with the Western look, and this image has male and female both. So we can see if the face was swapped with the Eastern female, then the result was best, and for the female. But for the male, if it was swapped with the male Eastern face, the result was good. These are the scenarios which we have captured in our own data set. These are captured our own data set. So we can see the best result was when the female face was swapped with the female face and the male face was swapped with the male faces. So here the male faces are portraying the correct result. And that's all. Thank you. So this is all about the presentation demonstration from our side. I think I have gone through within the limit.
Okay, thank you so much, Dr. Mishra, and it was really very informative.
Thank you, Professor.
So I hope Professor Kim is here, right?
Yeah. We both are here.
Okay, so we need to have few discussion. Maybe we'll take few questions from audience as well. Meanwhile, okay.
Okay.
So what we were planning, like we can have a short discussion, panel discussion kind of thing. You both can join at that particular end, right?
You can release.
And
we can share.
okay, so just following the lectures, your like Dr. Mishra's and Professor Kim's lecture. So I have let's start with the few questions, then maybe we'll discuss about it, right?
Yeah.
Okay.
So Professor Kim, I have a very short question, right? Maybe you can answer it. So the very basic question, as we know, in many developing countries, it's not very easy to get a very well-defined road, right, where you can enable autonomous vehicle, right?
Mhm.
So in many literatures, we saw people are talking about the concept of flying cars, right?
Mhm.
So how do you see the future of smart transportation from today to maybe next 10 years or 20 years? Do you think there is the concept of flying cars and other aspects will also come into the picture? What's your opinion at all?
That issue is now we are starting to.
Yeah, we are already going through that. There is payload vehicle, the autonomous drone taxi.
Mhm.
So in Professor's slide and in my slide as well, you have seen that there is already drone taxis, which is we will see in near future, as you are saying.
So we call it for UAM, urban air transportation.
No. So the other question could arise: how you are going to manage the air traffic?
Yeah, that is actually very important issue. Actually, we are concerning for 6G.
Yes.
6G enabled the UTM. UTM is urban traffic management system. Currently, the most of cellular communication is for the base station is directed to the ground, but all the air vehicle is flying above the 100 meter to 500 meters. That range, the current cellular or the 5G is not covering this area. That we need for the satellite-based system. Then the satellite-based, the low altitude satellite is a basic the component of a 6G. Then we think that in the next decade, but we in the 6G roadmap, we will be commercialized in the 2030. Then I think can be almost synchronized for UTM and the 6G new technology we're combining. Then it can be the 6G the autonomous UAM will be in the future in the next 10 years for autonomous air mobility will be. You can see, yeah. For big city, traffic is very severe. Yeah, then you can enjoy for.
So the other maybe other question. So do you think is there any need to build a dedicated lanes for the autonomous vehicles in expressway?
Actually, maybe in the beginning, but eventually, I think it can be a mixture of a human driving vehicle and autonomous vehicle. I think no need for the autonomous vehicle lane. Separate
No,
autonomous
so
vehicle.
if you take the example of many developing country, maybe if you go to the European country, right?
Mhm.
So it's very difficult to even get the lane for your car, right? People will cross from anywhere. You never know, right? From which side people are. Even in India, you'll get a lot of cows as well, right?
Yes,
You
I
never
think
know from which side
we
they will
need
come.
level.
So you will always be stuck in somewhere. It's really impossible to move ahead.
I think the air will be faster.
Yeah.
Air you can make the lane in the three-dimensional, the layer by layer. But in the two-dimensional, there's a limitation in space. But the air we can extend by layer, then you can obtain more lanes. But if your positioning and the localization technology is more accurate, you can get more lanes.
It has other advantage as well, that there will not be any pedestrian or something, so we can get rid of that as well.
No. So it's very difficult to get the. You cannot get rid of the pedestrian, right? Dr. Mistra, I got to know, like, you're from ITBHU itself, right?
Yes, yes.
So just go outside of the main campus of ITBHU and see. Do you think your car would be able to move even a single feet?
Yes. You're
Okay,
right.
the reality is another aspect, right?
Yeah, right.
So maybe the one last question from my side, then we'll take few questions from the audience as well, right?
Okay.
So there are many beginner in our audience right now. So just give a big start. So what are the effect of AI, actually artificial intelligence, implemented in autonomous cars? So what particular direction can you give it to? Maybe for the basic, from basic to the advanced level, the person who is looking to exploit the concept of AI into the autonomous domain.
Actually, autonomous vehicle is a big platform, but all kind of the AI technique for the image recognitions, for natural language recognitions, also the reinforcement, all kind of technologies are required. But there is the mandatory requirement is for the safety issue. There is there is a functional safety in the autonomous vehicle system. There is also the standard with for you call the SOTIF, safety of intended function, is for the safety criterion of artificial intelligence system. Then every in the autonomous vehicle, this kind of the safety is applied in addition to the normal the AI for the mobile phone and the other the commercial application. That's why eventually I think the AI for autonomous vehicle is for the top the state of art technology.
It has become this synonymous thing, like computer vision. Earlier it was there, but nowadays any kind of video and image processing task is synonym to the autonomous vehicle, I think so. In terms of image process, artificial intelligence based image processing, it is the synonym of the autonomous driving itself.
No, but there is slight variation as well, right? If you see the concept of latency is not pretty much important when you're going to talk about the image processing and the car set.
Yeah,
but in autonomous vehicle, latency and accuracy is pretty, like, they play a very important role, right? We cannot rule out the quality requirement and accuracy at the same time, right?
Exactly.
So even a certain
fraction of second or millisecond is
it may be dangerous for anyone, right?
Right.
Yeah.
So let us take few questions from audience side. I can see one question. Rudransh, you can directly ask your question, right? You can mute yourself and ask your question to the professor.
Yes, sir. So can I ask now?
Yeah, you can.
Yes, sir. Good morning, sir. So I have a question, like, regarding what you think about, like, the technique of MITs, like self-driving car, like the way they are collecting the data from a 3D simulated environment, and that 3D simulated environment is with of GAN set size. And then they are using reinforcement learning in that 3D simulated environment, collecting the data, collecting the different type, collecting the data, and then using that data. They are then using that data to train their self-driving cars neural network, and then they're using on the real life scale. Like if this approach is so efficient, and like why other companies like Tesla and other institutes that are making self-driving car, why they aren't using these techniques? Like is this technique actually efficient? So
Professor Kim, did you understand the question, or should I explain it?
Asking that there is some simulated environment data set and real environment data set.
Okay.
So is it good to go with the simulated environment data set or with the real environment?
Then usually in my slide, we are the pre-training phase, in the final training phase. Usually we use a simulator for the pre-training, but for the actual implementation on the real vehicles, the simulation cannot consider all the possible situation, and then the image quality, and there are many different things. Then simulation only provides the validating the initial model, but the final the validation we need to validate in the real vehicles. Then for simulation, most of the paper and the academic research is about the limitation of budget and the limitation of time. Then we are doing usually on the simulation, but for real implementation means for a lot of the investigation on the real vehicles.
I would like to add that, as you said, the two scenarios, the MIT is the academic institution and Tesla is for the commercial and industry platform. So as professor said, that the thing is, in simulated environment, you are saving the cost of collecting the data set. If you have industry to collect it, because data set collection is very huge task and it requires very much amount. So for academician, it is not means feasible to implement such a huge investment. But Tesla can do the same thing because it has their own platform, several vehicles they can implement the onboard equipment for collecting data sets. So they can do. But as professor said, that safer way is to go first with the simulated environment, because there you can collect data set in simulated environment without any huge amount of investment, and then just retrain, as you already told that MIT is going for that. Everyone, I think in academics, it is the better way. Use both. First collect data set from the simulated environment and then retrain in the real environment the exact model you are asking about. I think...
So maybe
yes,
I will also add one more concept into it, right? So in the simulation environment, you can crash your car as well, right? Any problem. But in reality, if you are going to crash your car, it would be very dangerous, right? Okay.
So like one more question I have, in relating to this, what do you think about the technique of reinforcement learning that they are using? Like instead of using like a simple CNN or then other combination of other neural networks, like how they are combining the reinforcement learning with like computer visions?
Yeah, for reinforcement learning is for, that the supervised, unsupervised, reinforcement is three main category of learning. But that currently the reinforcement learning facing a lot of the problems. I don't have enough time. I don't think I have enough time for explaining what the details of reinforcement learning. Right now, we are challenging the learning technique, beyond the reinforcement learning. The supervised, unsupervised, the reinforcement learning is a method in the textbook. Then in the real world, there's a more advanced approaches. Right now is going on. Then basically the simple reinforcement learning or the unsupervised, supervised learning cannot solve the complex problem in the real environment. That's why there are many new ways. There are many new, and there are the many shortcomings of reinforcement learning itself. Then you can solve a very static problem very efficiently, but for the dynamically changing problems, or rules are changing. There are many the unseen environment conditions. We facing this kind of situation in real world, but reinforcement learning cannot solve this kind of problems. That's why we are learning method. New learning rule is another area of research.
Yeah.
For then also the autonomous vehicle and the mobility is very important for this kind of new learning way. Because of static learning, we have a lot of data itself, but autonomous vehicle is very dangerous in real environment, the real experimental situation. That's why we are very careful, and we need more the learning method for the autonomous vehicle. That's why it's autonomous vehicle, as I told you, will be new platform. It's for leading the AI technology to the new way of the algorithms or new way of learning method.
That's right. That's right. And now I think it's in the initial phase, it's impossible to capture all the aspects, right? You might be trained, means maybe system is trained with different kind of aspects. Maybe you trained your system with the buffalo, with the cows, but with what? But what happens if goat is coming in on the way, right? That is another aspect. So we need to make our system more intelligent, but it's iterative process. We cannot do everything within one shot.
Yeah.
Right. So we have few more questions, but we are lagging with time. So maybe I will just go and thank to everyone. So dear speakers, attendees, and staff of teaching, learning, and team IIT BHU specifically, thank you so much. On behalf of coordinator Dr. N.S. Rajput and IIT BHU Varanasi, I, Dr. Ajay Pratap, co-coordinator of this program, would like to convey my sincere gratitude and thanks to everyone for being the part of this program. We have been together for last almost 6 days, and specifically today is the day to be thankful and to be inspired. First of all, we must be thankful to our renowned speakers from around the globe and finding a time for us from their busy schedule. Here in this short-term course, we have received a great learning platform to apply in our research objectives for betterment of societies. Dear attendees, now if you can notice, I would like to know that what a gift it is to be as renowned speakers from academia as well as industry, because not all short-term course offers such an advanced version of deep structured topics. I am also thankful to Cisco India for their cooperation and coming together for this short-term course, and I strongly believe that your support will always be with us in the future as well. Finally, I would like to thank the staff of teaching learning team IIT BHU Varanasi for being here from last 6 days, even above all being in the time at the weekend, especially when the Holi is knocking at the door. Okay, I want to extend my generous thanks to the entire team for their support and cooperation. Thank you everyone, and may this festival for colors filled with colors in your life. To every shade of you, I wish happy and colorful Holi. Thank you so much for being here, and happy Holi once again. Thank you so much.
Thank you, Professor.
Thank you so much. Okay, bye bye. Thank you, Professor Kim. Thank you for your time and cooperation as well.
Thanks very much.
Yeah, thank you so much. Bye bye.
Happy Holi to you all.
Thank you so much. Bye.